Hello everyone, my name is Chunhuan. I come from Harbin Engineering University. The title of my presentation is a novel Chunhuan Microstructure and Properties Technique for Metal Additive Manufacturing Assisted with Ultrasonic Energy. The outline of my presentation includes 4 parts. Let's move on. The first one. That's the background about the history of investigation on how to improve the microstructure and the properties of metal additive manufacture. As we all know that there are many alloys fabricated by additive manufacturing methods, of which microstructure is always showing the large size columnar crystal. In this way, it's obviously influenced on their mechanical properties. For example, for the austenitic stainless steel, the strengths of additive manufacturing parts are higher than that fabricated by traditional methods, while the parts have low ductility and obviously an isotropy, which limits the application of AM in the engineering fields. In order to make clear the reason for the columnar crystal during the additive manufacturing process, there are many references with respect to investigation on the main factors for determining solidification structure. The main factors are temperature gradient, solidification rate, and undercooling. This figure shows the relationship between GR and microstructure under different conditions. It can be concluded that the low G division R and high G multiply R is favorable for exquisite crystal formation and grain refinement. How to obtain the condition during AM process. Up to now, there are many methods to try to solve the problems which always occur in additive manufacturing process. They are optimization of forming process parameters, post-processing methods, alloying and particle strengthening methods, rolling methods, external energy field assistance. The direct method is the optimization of forming process parameters. Following the optimization of forming process parameters for select laser melting method, the tensile strength of AM parts are higher than that fabricated by traditional methods. The traditional heat treatment methods are always used to eliminate the defects and improve the properties for metal alloys. These methods are also used in the field of additive manufacturing. By the most processing methods, the microstructural parts can be improved, especially for the large grain or columnar crystal. The other methods are alloying and particle strengthening method, which can be improved the mechanical properties, while it will change the pounds of materials types, which may be influenced on the other properties of materials. Based on the mentioned above methods, there are some researchers proposed the rolling method for additive manufacturing process. However, there are some limitations for rolling rolling processing. Higher pressure is required, not applicable to thin-walled parts. The shape and size of the roller are fixed, which is not suitable for complex components which are uneven wall thickness, not applicable to components with complex cavities. For the external energy field assistance, there are magnetic field and ultrasonic energy field assisted with AM. Both of them are effective on refining the microstructure materials. For example, for the stainless steel, the grain size of microstructure can be refined and the texture is improved. Therefore, based on the research history of how to improve the microstructure and the properties of additive manufacturing, propose a novel technique properties to solve the large size of columnar crystal. That is to say, during the additive manufacture processing, the ultrasonic is synchronized with additive manufacture, which can be realized the ultrasonic dot effect. It means that on the one hand, acoustic cavitation and acoustic flux effect on the multiple. On the other hand, ultrasonic influence on the deposited layer with higher temperature using the recrystallization. According to the new idea how to using the ultrasonic double effect during additive manufacturing, which is dependent on the design, the ultrasonic vibration device. In order to prove the new idea, we use the finite element method to simulate the process of ultrasonic effect on the additive manufacture multiple. It can be shown that the acoustic intensity can be reached the ultrasonic cavitation threshold. In this way, when the solidification occurs, the acoustic cavitation will affect the dendrite regimentation. As a result, the refined grains can be obtained. The introduction of ultrasonic vibration will have a great impact on the temperature field of the melting pot during solidification. This is mainly due to the introduction of ultrasonic vibration, which causes the alternative of positive and negative pressure in the melting pot. Thus, the ultrasonic intensifies the flow of melt in the melting pot, makes the temperature in the melting pot more uniform and the cooling speed faster. The temperature gradient at the liquid-solid interface decreases and the solidification speed increases after ultrasonic vibration affected. After ultrasonic vibration, the melting pot has a lower G division R and high duration solidification G multiply R. It's easier to obtain final exit crystal structure in ultrasonic vibration metal melting pot. Ultrasonic vibration can effectively promote the transformation from columnar crystal to quasi-exit crystal in the melting pot and expanding the quasi-exit crystal area at the top of melting pot during solidification. According to the simulation results, we designed an innovation structure of ultrasonic impact device. In order to obtain the ultrawave in the melting pot, the hull is rigidly connected with the impact head. In this way, there are many advantages of innovation structure design now of ultrasonic impact device, such as increases the impact frequency, improved energy efficiency, increased ultrasonic action depends, and so on. Based on the series, we manufactured the ultrasonic impact device and got the United States patent and Chinese patent, and we got some results for additive manufacture assisted with ultrasonic vibration. The introduction of ultrasonic vibration refined the microstructure of stainless steel and promotes the transformation from columnar crystal to a quasi-axis crystal in the melting pot, and the ultrasonic vibration affects the height of the deposit layer. This decreases the width, increases, and the contact angle decreases. After ultrasonic vibration, the post-columnar crystal in the deposit layer disappeared and was replaced by uniform and fine equiaxis crystal structure. The effect of the ultrasonic vibration can be effectively eliminated the columnar crystal, improve the uniformity of the grain, and refine the internal structure of the deposit structure layer. In this way, the texture strength of stainless steel has been weakened and are all eliminated effectively. Therefore, to a certain extent, the ultrasonic vibration technique can improve the isotropy of stainless or steel components fabricated by additive manufacturing. The plastic deformation on the top of the deposition layer caused by ultrasonic vibration introduces a large number of small angle grain boundaries and lead to a large increase in KAM value and dislocation density in this area. The influence of ultrasonic vibration on dislocation is not limited to the small ridge at the top of the deposit layer that produces severe plastic deformation. In the depth direction, ultrasonic vibration will still improve the dislocation density in the deposit layer with a certain range, which can be predicted that the depth of ultrasonic vibration on the dislocation density can reach 0.7 millimeter or more. When ultrasonic vibration is not applied, the GOS distribution of most grains is between 0 to 1, reaching 44.5%, which means that the internal orientation of this part of grains is small, which can be considered as low strain. However, after ultrasonic vibration treatment, the grains within the range of 0 to 1 at the top of the deposit layer almost disappears, and the grains with GOS distributed between 0 to 1 in the whole range were only 34.4%, reducing about 36.9%. The grains producing high strain are connected on the surface of deposit layer, and the strain effect zone exists to the area about 0.7 mm below the surface. After ultrasonic vibration treatment, the overall micro hardness of the deposit layer was improved, and the average micro hardness increased by about 10.7%. The introduction of ultrasonic vibration can interrupt the epitaxial growth trend of the original columnar crystal, refined the structure of titanium alloy manufactured by Additive Manufacture, and promotes the formation of excited crystals in the deposit layer. Finding equiaxis microstructure, texture strength of the deposit layer can be weakened by the ultrasonic vibration, the solid phase transformation of metal alloys cannot be affected by ultrasonic vibration. Through the introduction of ultrasonic vibration, the strength of the titanium alloy is improved. Meanwhile, the plastic of the titanium alloy is also improved to a certain extent. It can be concluded that the above results can provide a strong support for the application of the ultrasonic vibration in the field of additive manufacture. In the first part of the I will introduction application of ultrasonic energy in additive manufacturing based on the innovation design of ultrasonic impact device. The lead field additive manufacturing equipment acquisited assistant with ultrasonic vibration and large gauge has been developed. These apparatus include Dow laser field additive, ultrasonic impact, online detective, CNC milling, and other functions which can achieve online control of microstructure and the performance of additive manufacturing structure parts and shape control, integrated rapid prototyping manufacturing of large-scale complex structure parts. The titanium alloy components with integrated forming by additive manufacturing according to the effect of ultrasonic energy fields. The microstructure has been found and the residual strength has been eliminated, which can be improved its pressure resistance. Therefore, the conclusions of my presentation are proposed a new idea with respect to the ultrasonic double effect on the deposit layer during the additive manufacture process. Analyzes ultrasonic vibration effect on the microstructure and properties of different alloys. Investigation of the mechanism of ultrasonic effect depending on the acoustic cavitation and acoustic flow effect affected on the melting point. Using this theory of ultrasonic energy fields, the typical components have been fabricated by additive manufacturing, which indicates that this method